Hi, it's Terry Dennery of the MathWorks. So I'm going to do a bunch of math and science homework problems, and I'm going to begin with the problem we're looking at right here. Right, and so I'm in PowerPoint, and I'm going to kind of put it into slideshow mode. It's kind of where I want to get started. Right, so it's a classic problem, pretty straightforward. Basically, a box sliding down a plane. We have the angle of inclination of the plane at theta, and essentially we got gravitational force acting vertically to drive the movement. All right, and I'd say the trick to this problem is really kind of figuring out the right, you know, coordinate system. And so we're going to choose the x-axis to be parallel to that plane, and we're going to use the y-axis to be perpendicular to that. All right, and with that, we're going to be able to get these very useful calculations for the y component of gravitational acceleration as well as the x component. All right, and this might look a little bit tricky. How'd you get that? Well, if you do your geometry, you're going to kind of recognize there's some very useful right triangles in here, and we'll see that, well, if this is theta, you know, this angle between the vertical and the plane, well, that's going to be 90 minus theta. And then you kind of notice, well, the x-axis and the y-axis add up to 90 degrees, and so the complementary nature of this angle with this, well, it leads us to understand very cleanly, quickly, that angle will be theta. And knowing that that's theta, then we kind of understand the projection of theta along that y-axis. Well, that's going to be a cosine, and the projection along this opposite, you know, well, that will be the x-axis, right, or the x component of g, right? And so other parameters that will be important will be the mass of the block, the angle, which is in this case 30, and then the static and kinetic friction coefficients. And so I kind of like this picture, and I like it so much, I'm going to take a picture of the picture. Right? And so let's just kind of copy this. Okay, and now let's go to MATLAB. And we're going to do this with a live script. And live scripts are great because we can put pictures in live scripts. And so that's kind of in our text mode, and we'll just hit Control V. We'll paste that in. And we'll just resize that. That looks good. Okay. And so now let's start coding. All right, and I'll begin by just kind of bringing in that data. M is equal to 10. I'll suppress the output. That means it won't show up here on the right. And I will put in a comment that that's going to be in kilograms, kg. All right. Now theta, let me call it theta degree, will be equal to 30. And my first calculation will be, well, let's get that in radians. Now I practiced that, that's why these numbers are already in there, but let's go ahead and kind of go through the motions on this. And so theta degree times pi divided by 180. All right. And it's kind of bugging me so much that all that stuff's there. Let's go ahead and clear my workspace. All right, so it's now empty. Where's my live script? Here it is. All right, and let's get the friction coefficients in there too. So I'll call it mu. Oops. Stat is equal to 0.3 mu kin 0.2. All right. And now let's get that gx and gy in there as well. All right. And I'll go right up here, kind of like defining gravity at the top. So g itself will be equal to 9.8. So with this, we got gx is equal to minus g times sine of theta And the whole point of getting in radians is that MATLAB likes to do sines and cosines with radians, not degrees. All right, that let's do a calculation. We'll hit run, and that all looks pretty good so far. All right, and what I'm going to do now is go back to that PowerPoint right here, and on this page, we basically have all the questions that they're asking us. So let's copy all that, Control C, and get back to our live script. So this is the thing I really like about live scripts, is it allows you to talk like a human being. It also allows you to talk like a computer. So that ability to kind of go back and forth between, kind of like, verbal documentation and coding, I think is very convenient. In my opinion, if I had this when I was in college, I'd probably done all my homework assignments with this. All right, and so our first question is, what is the static friction force on the block? Well, that's kind of a trick question because we don't even know if there is any, and it really kind of brings our attention to what is a static friction coefficient, right? And what it is, I think we might be familiar with the formula, and so let's go ahead and get that formula in there. And let's say static force. It's really a limit. It's about as much as it can take, and it's equal to mu stat times n. Right, so what's n? Let's see if I got this. Right, it's using zoom it. Right, it's the basic idea, that the plane exerts a force on the box, and we generally call that N. All right, and so the forces on the box really are going to be the gravitational acceleration, at least in the y direction. That's why we went into y and x components. The gravitational force in the y direction plus N are going to be equal to the mass times the acceleration in y. But because there is a plane there, and that plane applies the constraint that the box cannot move through it, we know that essentially that acceleration is equal to 0, right? And that what it really does for us is allows us to easily calculate n. And so I'm just going to say n plus mg y, well, that's equal to 0, therefore n is equal to minus m times gy, right? And so we'll run that. Okay, and we see that that static force limit will be about 25 newtons. All right, and so now we got to find out, well, the forces that are trying to move that box, are they bigger than that? I mean, this is what gx is for, right? The m times gx is going to be the force that's going to be trying to move it down the plane. So I'll call that driving force. It's equal to m times gx, and we'll hit run one more time, and we'll see it's equal to minus 48.99. Now, I'll just kind of call it out that what we're really doing is setting I'll call it an absolute limit, and the static or any kind of friction force is always going to act in a direction that's kind of defined by the rest of the mechanical dynamics. And since the block wants to move down the plane in the negative x direction, while the applied friction will be in the positive direction. And just to kind of really be maybe a little bit more clean and efficient, what I'm really saying is it's the absolute value of 48.99 that matters, and that's way bigger than our static force limit. And therefore, the box absolutely will be moving down the plane. All right. And so with that, we kind of have our first answer, which is there is no static friction. If you wish, we will say it is 0. Okay, all right. And that looks pretty good. And I think for these kind of word answers, I'll also just put those in italics so they look a little bit different than the questions. All right. And let's see, how are we doing on time? I think I'll kind of wrap up on this. So we really did kind of part one of this. We'll just kind of do a couple more videos to kind of get the next two. So I'm going to try to keep these kind of around the length of about 10 minutes. So we've done part one.